Right, good morning, good afternoon, good evening to you all. This is the latest in the Beyond Modelling webinars, the series of webinars looking beyond witness modelling at some of the other areas of project work with simulation. This particular webinar, I'm Tony Waller. I'm going to be talking to you about witness and Six Sigma, and in particular an example on using the new experimenter and optimization in a Six Sigma context within that. If you have any questions during the session, please use the chat mechanism. I have somebody collating questions and I'm happy to answer that at the end of this session. It may be this is a slightly shorter one than the half hour. There's limited material to get through with you, so there might well be some time for a little two-way dialogue. So we'll see how we get on with that and where we get to. What I'd like before we start with the optimization example is to do a little recap of some of the other Six Sigma functionality that's inbuilt into Witness. And I better just close my mail, otherwise I'll be getting in certain other mail messages as we go. Here we have a model that I'm running in Witness of a production line. And one of the things in this model is that one of the operations has a certain percentage output to scrap. And this may not be the only option in this model, but there may be other options as well. Now, when you look at the key statistics of the parts at the end of a run, one of the things that is reported is a sigma rating in the far right-hand column here. This translates the number of units which have been scrapped into a defects per million opportunities, which is the classic kind of way of recording a Six Sigma rating, and turns that into a Sigma rating score. So 7 scrapped there out of the 353 that have been shipped, 7 have been scrapped, and that translates into a Sigma rating of 3.57 for the part, based on those which have been pushed to scrap. Now, that isn't the only rating that you can have, though, in a witness model, because we have a number of functions in there which help convert any defects per million opportunities figure into a Six Sigma rating. And I'll show you how that's done by using the immediate actions toolbar. This is the model toolbar, which I've opened up from the toolbar, and I've got it floating just to make it easy and clear. While I'm looking at this, one thing that people often ask me is, how do you make this box bigger? That's simply done by going to model user commands, and when you're in model user commands you can click on that box and you'll find you have the ability to make that box as long or as short as you wish it to be, and to move it about on the toolbar. So there are many different ways to rearrange the toolbar in that way. When you close the customize box here, then that's how your toolbar will stay, and you have a lot of space then to write, maybe more than the standard space, to write your commands in there and then run them using the other button here. So what I want to do here is, firstly, I'd like to show you the way in which you can get that part Sigma rating, which is taking taking notice of the numbers which have been scrapped, how you can get that out of Witness. If I put in here print part Sigma rating brackets part A, and when we go to the interact box here at the bottom and we run those actions, you can see that it's returning in the interact box a figure of 3.56897 as the Sigma rating. And that correlates exactly with the figure, slightly rounded, as it's reported in the Sigma rating statistic here. But as I say, you're not stuck with only being able to report scrap rates as a defect in a witness model. you can come up with any measure of success, any measure of defect. And one thing that I've done here is I've taken another statistic here, and I'm recording how many parts take under 10 hours to go through the system and how many parts take over 10 hours to go through the system. So this is, if you like, a certain service metric in this model. And I'll just run this on for a while. In fact, I'll batch it on to a time of approximately 200,000 time units here. We have roughly one part coming in each time unit, so we'll have approximately 20,000 parts coming in, I think. Part coming in every 10 time units, sorry. So we've got approximately 20,000. Let's just run it on a little bit more. And in those 20,000, 200,000 time units, we've had about 20,000 different samples come through, of which 61 have been outside our service criteria. Now, if I go back to our toolbar again, we could find out what is the sigma rating for that by using the sigma rating function rather than part sigma rating. And what we have to give it in as an argument is the 61 defects that we've had, but we need to multiply that up to be numbers of defects in 1,000,000 opportunities. Given that we've had approximately 20,000 opportunities, we need to multiply that by 50, and we can nice and simply put it in 61 times 50. And if we print the sigma rating for that, you can see that that in the interact box comes out at a sigma rating of 4.24. So Witness has that it's a normal probability table inbuilt into Witness to furnish you with whatever sigma rating for whatever measure of success you want to use. Now, one of the other things that you'll have noticed on any of the reports in the statistics is we have a mini-tab button as well. And that enables you to output any of the statistics in Witness for further statistical analysis using Minitab. And the reason we put that in Witness is because that's usually, it's one of the main tools used by a lot of companies that do Six Sigma analyses. So I hope it's the one that you use. If not, you can still copy and paste the statistics out manually into a sheet. If you're using variables, you can also just select the variable, any number or array of numbers, and then on the report toolbar, then hopefully you'll be able to see we have a mini-tab button. It's slightly hidden at the minute by the fact that I'm speaking on my version here, but I hope you can see the Minitab button there to output to Minitab that figure or any array of numbers. Now I want to move on to an optimization example, and this is the model I want to use, and this model has quite a bit of explanation that I need to do about it to explain to you how it's set up. But essentially it's a sequence of 20 different operations, and I'll set it running, down which this line we are putting two different parts, P1 and P2. The operations are arranged sequentially, and the only buffer capability in the line is between operations 5 and 6 and operations 13 and 14, where we have buffers that have a capacity of 5 parts between those two operations. The operation is 20 long, and after the 20th operation, the parts are output and shipped. At the 10th operation, there is an option to go into a rework loop. Some parts travel into that rework loop, and then they rejoin the line after they've been through that rework loop. So there's a part now just going through that rework loop. Now, one of the interesting things about the way in which this particular model's been coded up is that it actually only uses a couple of machines. One machine for each of the 20 workstations in the main line, and one for the work loop for the 3 in the work loop line. And if I double click on that machine, you'll see it's got a name WS standing for workstation, a quantity of 20, And the input and output rules work for each of those different 20. So if we go into the input rule, we can see that if it's the first machine in the line, for example, here, if n equals 1, then it's pulling a certain percentage P1 out of the world and P2 out of the world. It's pulling 50% P1, P2. And the reason we're pulling whenever we need material here on this line, this is a model we're looking to establish what the theoretical capacity of the line might be. So we're saying it's never starved of input. But if n equals 6, then it's pulling from the first buffer. If n equals the 14th workstation, then that's pulling from B2. And all the rest, there are no pull rules at all. Let's look at the push rule, the output rules. If n equals 20, then the bottom rule here comes into force, push to ship. If n equals 5, it pushes to the first buffer. If n equals 13, it pushes to the second buffer. If n equals 10, a certain percentage go around the rework loop. But most of the workstations simply push to the next workstation in the line, WS n plus 1. Now we make a lot of use of n in this model as well in the breakdowns section, where you can see that the time between failures is based on a uniform distribution based on the value n in a variable array, minus 50% of it and plus 50% of that value. So we have a breakdown frequency in a BF array, and we're taking 50% off of it, adding 50% on, and we're saying the time between failures is equally likely anywhere in that range. And all repairs, you'll notice, are done take between 5 and 10 minutes. That's not dependent upon the value n. The cycle time too will be dependent upon the workstation, and we've read in from Excel 2 arrays. Here's the one for cycle time 1, which is the cycle times for part 1, P1. In the actions on initialize, we have a simple Excel read array from 20 different cells in that Excel spreadsheet into the variable CT1. Those are then displayed on the graph here underneath, in the table here underneath the respective workstation that they apply to. So the cycle time for part 1 on workstation 1 is 3.18 time units. And the cycle time for part 2 is 2.11 time units. These are the breakdown frequencies. And what we can do is now, I'll explain the other 2 arrays there in just a moment, but let's just batch this for a while. Let's batch it for about 1,000 hours, about 60,000 time units, and let's look at the statistics for this production line. We've made about 12,500 parts, or 12.5 parts per hour, something like that anyway. If we move on to the machine statistics, I think this is quite helpful to look at as a chart, and I'll just maximize the size and we'll put all the different operations on there for you. Now from this chart we can see that there's a lot of green on the chart, which is the busy time for the different machines, but there's an awful lot of magenta colour, which is showing that a lot of the workstations are blocked for a significant amount of the time. We can see that the rework loop, which is the top 3 rows, is not used very much on this line and therefore is unlikely to be a bottleneck. But it's quite difficult from the other lines on this chart to work out exactly what the bottleneck on this line might be. And that's because you have the busy time and the blocked time, and you don't know for the ones which hit the end here whether if they were blocked a little bit less, then their busy time then their block time would turn into idle time, or whether it would turn into busy time. So they're all dependent upon each other to a certain extent, and for that reason it's quite hard to see what the bottleneck might be in this particular instance. It's common in many companies to take a production line like this and to try and work out how to improve that line But before doing projects that would concentrate on a particular operation in that line, then a company might write a witness model like this to establish what is the benefit of improving the cycle time or improving the breakdown frequency on a particular operation. Because there's no point on doing an improvement project on a particular operation if overall that operation is not going to contribute to a better jobs per hour through this particular production line. So a company will often use a model to try and work out which are the operations to concentrate particular, say, Six Sigma improvement projects on, and those projects can then look at the machine programming, can look at the maintenance cycles, etc. for a particular operation and see what could be improved. But the model has said focus on that operation, and that operation will give you the maximum bang for the buck. Now in this particular model, we have an expert online as well. We have somebody who's been through and looked at the operation or has experience of each of the operations on this line and has assessed on this improve array what percentage improvement they think it might be possible to make to the cycle times of the two parts on that particular operation. If we look at operation number 19 over here, the person has assessed that there might be a 12% improvement made. Maybe that's because that operation really hasn't been looked at for years. And maybe that, that because of that, there might be a lot of things that could be done to improve that one. Whereas operation number 3, there's really only room for a projected 1% improvement. And that might be because that operation has been analysed to death already. People have spent a lot of time looking at that and already done major improvements and made major improvement in that cycle time. Now, so what we're going to look at is the potential of improving each of the cycle times by these percentage points. But we know that we're not going to be able to analyse or have the time to do a Six Sigma project on each of the operations. So we want to choose which are the ones which have the most effect. And that's where the witness experimenter is going to come in. And I've defined this other variable array here called set factor. And when I set these values to 1 in the set factor array, it will apply the particular improvement on the particular operation. So if I set factor 5 to 1, it will effect a 5% improvement on the cycle times of parts 1 and 2 at operation 5 only. Now the calculation for that is done in the cycle time function, which is in the machine, which if type equals P1 returns CT1N, and then if the factor's applied, it will apply that improvement. It will take that away from the cycle time. If it's P2, then it will do exactly the same to the CT2 array. So we're choosing here to set a number of factors which will affect the improvements on the cycle time for those machines. So let's go into the experimenter. And let me open up an experiment file that I have set up for this. And you will see that we have 3 lines here of parameter ranges or sets of values that we've set that can change. And the first line is simply each of those 20 numbers in the set factor array. And I've said they can be either 0 or they can be 1. And that's for each of the 20 array items. I've also said that the buffer capacities could be increased from 5 to 6. Notice I've also in square brackets there got the number 5. That's important when you're running Six Sigma because the suggested value corresponds to the current value. So when you're using a Six Sigma algorithm, if you want to define what the current position in the factory is, then use the suggested value to set that up. And that's also set for the set values where they're all set to be 0. The suggested value is set to be 0 for that entire array. Now our response that we're interested in is simply jobs per hour, and if we go into where that's set up, you can see that's just simply number of parts shipped of P1 plus the number of parts shipped for P2 divided by 1,000. I've divided it by 1,000 because my run time, if you look up in the run length in the properties, is set to be 60,000. Essentially it's returning a jobs per hour figure. Now the optimization method we've established, we've picked here from in the properties is the SixSigma option, and what that does, if we click on the settings for that, it enables an intelligent algorithm, but you can limit the number of parameters that will change per run. And here I've just said limit that number to 2. I only want to try 2 different changes in any particular model run. Now because I'm doing only 2 changes, that means I've got time to run all the Six Sigma combinations, because I've got time to run all the ways that you can perm any 2 from 22 different variables. If I didn't, I'd be searching, if you see in the top toolbar here the number of scenarios, I'd be searching in a solution space of 4,194,304 different experiments, which is fine, but if you've got time to run it, the Six Sigma algorithm will actually run all the different options. So let's turn on the objective graph. Now I've pre-run this to a certain extent, and it will run the first 150 or so experiments here very quickly for you so you can see how the graph builds up. And here we're improving from a baseline figure of about 12.7 jobs per hour, and we're improving that up to the point where we're now above 12.9. And as this is running now, it's actually running Witness in the background right now. And you can see that now it's up above 12.95 jobs per hour. And in one or two more iterations, it will hit the absolute maximum that it finds in this particular run, which is about 13.05 jobs per hour. And if we go to the full results table while this is running, I'll just close that graph now, we can sort the jobs per hour figure in the jobs per hour column here to bring that top reading to the top, or bring the best reading to the top. And what Witness does is it shows you which of the factors that have changed in that to 1, and it highlights which have changed from their current value. So here we can immediately see in this top line that the ones in blue, and the color choice is entirely up to you. That's also set on the configuration grid in the others in this side here on the grid here where you set up the run parameters. You can see that the ones in blue here for that top column, for the top row, are factors 8 and 12. And that tells us that if we can make the improvements that the expert thinks we can possibly make for operations 8 and 12, that's going to have the biggest benefit in terms of jobs per hour through this production line. Now, when you've run I'll just stop the model running here for a minute. When we've run all the different options, we can look at what's called the parameter analysis grid, and if we sort that by percentage benefit, then you'll see that the top 2 are factors 12 and 8. This is the percentage that their runs on average with that parameter set have been over the worst one which have been found. And this helps in a crude way to rank all the different factors and tell you which ones are having the most effect. So if we were able to say not just make 2 changes to the line, 12 and 8, but maybe 13 would be the next one to try as well, because that's third in the list here. So the 13 might well have also an improvement in the run. We obviously have different charts and things as well here, and if we want to, we can run different numbers of replications. So now I'm going to run the same experiment but just with a lot of different replications, and when we do that, of course, we get box plots coming into the analyses. And you'll see that the result really is very clear again. The same set of result here is clearly better. 8 and 12 if we zoom in on this area here, you can see that the 8 and 12 change here actually produces on average a slightly better than 13.05 jobs per hour. The average is somewhere nearer 13.07 on the box plot, but we can see that all the readings really, from a minimum of 13.02 up to a maximum of 13.09, are that's clearly the best set of results in that instance. And because we're running replications, you're able to get the variance charts, and you're able also to, if we sort the best answer to the top here, we could select that, and we could get a confidence chart for how confident are we that if we make those changes, and that is the improvement in cycle time, that the jobs per hour will be somewhere between 13.03 and 13.12. We're 99% certain that true value is around that particular area of instance. Now, that's really the end of the presentation, but if anybody has any questions, please share them by chat, and they will be brought into the room here for me to have a response to. I'll just wait a minute while people give you a chance to ask any questions you might be interested in. But I hope by now this wasn't a basic presentation of the Witness Experimenter. There is a good canned half hour on that in the on YouTube on the Witness Simulation channel, and please have a look at that, and have a look at any other of the presentations which are available on that. Now, I'm being asked a question here by Jeff Cole. Thank you, Jeff. What about using an external DOE schedule to tweak the cycle times by the amount identified by the expert, and finding out the key drivers on the output via ANOVA and response surface methods rather than using an optimizer? Would that maybe improve on your results even more if there are any hidden interactions? Well, hidden interactions, obviously, simulation is testing out all those hidden interactions, but of course there are many other statistical analyses that you could do from a limited set of design of experiments, and I do heartily encourage use of DOE. Plot limited responses onto a surface and do what analyses in whichever statistical tool you can find to do that. Things like Minitab do this kind of analyses, JMP. There's huge amounts really on the SAS tools and the SPSS tools, offering many different ways to look at these different statistics. So yes, you're always trying to get a lot of information out of a limited number of experiments. What this will do for you though, and maybe I didn't explain this fully, with the Six Sigma algorithm on, here it was doing all combinations. But if we turned the number of options in the settings up to maybe 3 or 4, we may not have time to do all the different combinations, in which case it would apply the same heuristic search using the simulated annealing algorithm in here to learn from the results it's getting, and iteratively then to make the best choice of the next experiments it could do, searching the solution space using intelligence, and that works remarkably well in Witness. I really heartily encourage you to get to the to using the simulated annealing algorithm and the Six Sigma searching when you haven't got time to do all the options as well, which uses the same algorithm, and it's a remarkably effective algorithm. With a solution space of millions of different options as we have here, you would really only need maybe 1,000 or 2,000 for the usual well-behaved simulation model to find a true optimum, or at least very close to that true optimum. Anyway, thank you very much for your attention, and any other questions, please ask those by email, either to myself at twaller@lanner.co.uk or lanner.com, either is okay, or to the person who helped you set up the meeting. Thank you very much.